Next heading is electrostatic potential energy and electrostatic potential. What is the need for studying about electrostatic potential here? Simply, in order to explain a flowing water, we need a pressure difference. Why tanks are built over the terrace? Why can't we build the tanks in the ground? In order to make water to flow from one point to another point, we need a pressure difference. In order to create a pressure difference, tanks are built at higher altitudes. So water tends to flow from high pressure region to low pressure region. In the same way, if you want to speak about the movement of any object or any charges, we need to speak about the pressure differences. The electric pressure difference which makes the charges to move from one place to another place is called electrostatic potential difference, or in short we can speak about electrostatic potential. The amount of work that has been performed in making the charges to move from one place to another place is electrostatic potential energy. What is the need for speaking about this electrostatic potential and electrostatic potential energy? In order to explain the field around the charges in a very clear way and in a simple, elegant way. Explaining electric field due to various charge distributions on the basis of electric fields is much difficult, because electric fields are vector quantities. Electric potential, being a scalar quantity, is much useful and simple to explain about the same fields around the charge distributions. So we are going to speak about electrostatic potential here. As we know, the potential energies comes into play only in conservative force fields. In 11th standard syllabus, we come across this idea that the potential energies are defined for conservative force fields. As gravitational force is a conservative force, we spoke about the gravitational potential energies. In the same way, Coulomb's force is an inverse square law force. F is equal to K Q1 Q2 divided by R square. Coulomb's force is an inverse square law force and also a conservative force. So it is obvious that we can also speak about the electrostatic potential energies for this conservative force fields. So in order to speak about, or in order to know about electrostatic potential energy, we are going to speak about a simple idea that if a charge plus Q is placed at a point, let us say O, plus Q is placed, around this positive charge there will be a field. The presence of field cannot be seen, but it can be easily felt. As you know, existence of God cannot be seen, but his presence can be felt. In the same way, plus Q, the charge is there, around the charge there will be a field, the field whose presence cannot be felt, unless and otherwise you bring a test charge in such a field. Simple thing is that a campfire is there. Around the campfire, actually flames will be there. Around the campfire there will be a heat, and the heat will not be uniform throughout. Very close to the campfire, the temperature will be more, and as you move away from the fire or flames, the temperature will be less. So the temperature difference explains about the transmission of heat flow from one place to another place. As we saw in the case of gravitational force field also, if any object is said to be moving from one place to another place, then we need to know about the gravitational force fields. The gravitational potential energy difference plays the key role in explaining the movement of the objects. In the same way, in order to speak about the transference of heat, we need to know about the temperature difference. In order to speak about the flowing water, we need to know about the pressure difference. So one way or other, we can put it in this way, in this form, that the electrostatic pressure difference, which causes the charge to move from one place to another place, is called electrostatic potential energy. Electrostatic potential energy. So a positive charge plus Q is considered. Around the charge there is an existence of electric field, and in the electric field you are moving a test charge, let us say q prime, a positive charge, generally positive charges are considered, plus q prime is moved from a point R to a point P towards the source charge, plus q charge is said to be the source charge, q prime is said to be the test charge. A test charge must be moved towards the source charge in order to study about the potential around the source charge. So if you are moving a q prime charge, as I mentioned earlier, this charge is also a positive charge, then what will happen? As you move towards a positive charge will repel another positive charge. So this positive charge will be repelled. But we are exerting some external force on the charge to move against the force of repulsion. A Coulomb force will act, which will repel the test charge, but an external force which is equal and opposite to this Coulomb force will make the charge q prime to move from one point to another point. The magnitude of Coulomb force at a point distance r will be less. So the amount of external force that must be exerted over q prime must be less. As you come close towards the source charge, the Coulombic force will be more. So the external force what we have to spend over the charge q prime is also more. So at whatever point we consider, the external force that is applied must be equal and opposite to that of the Coulomb force, so that you are making the charge q prime to move towards the source charge. So what exactly is happening is a work is said to be done on the charge q prime by the application of the external force. In order to do this work, you need an external force here, right? So if the charge q prime is moved from point R to point P, then it must be moved in such a way that this q prime test charge must move with constant velocity. Constant velocity in the sense acceleration is 0. The charge should not get accelerated. It must be moved with a constant velocity. Why acceleration should be 0? If it gets accelerated, as you know, an accelerated electric charge will produce electric field. But we already studied in determination of electric fields around source charges, the test charge what we have taken should not disturb the field around the source charge. So it should not possess any electric field. Q prime should not possess any electric field. If the field due to Q prime also exists, the total field at any particular point will differ because of the presence of source charge as well as test charge. So the field around the source charge must be left undisturbed. In order to maintain it undisturbed, this plus q charge should not be accelerated. If it is accelerated, then definitely it will produce an electric field which will disturb the field produced by the source charge. Then the determination of fields will not be proper. So in order to avoid that, the charge q prime must be moved with a constant velocity, that is with zero acceleration. Then we can write the condition. If it happens, then F external is equal to F Coulomb, Coulombic force. The two forces must be equal and opposite. So what is the amount of work done on the test charge q prime? We can write here work done is equal to, as you are moving from R to point P, then we can write this as F external into dr vector as the variable. So we can write W equals integral R to P F external dot dr vector. So work done is not a constant. At this particular point the force required is less. At this particular point the force required is more. So at each and every successive point from R to P, the force is gradually increased. So if I divide this distance P and R with so many number of infinitesimally small elements of magnitude dr, then if a force F external is applied on a small element dr, or F external is applied on a charge q prime to move through a small element dr, then that will give you a small work done dw. So what is the work done in each and every elements? it will be dW, dW, dW. Shall we say the work done is same at all points between R and P? No. Work done here is less. It increases further. It increases further and further and further, and work done will be maximum at this point. As you move beyond P, work done will be more, because this Coulombic force will produce a lesser repulsive force at this point, because distance increases, force decreases. So Coulombic force is less at the point R, so external force that must be applied on Q prime is also less. As you move to the next element, the external force that must be applied is increased, because Coulombic force increases, because distance decreases. So as R decreases, Coulombic force decreases, or Coulombic force increases. So the external force that must be applied also increases. So work done also increases. So work done is not a constant, work done is a variable. Work done is changing at each and every successive step. For a smaller element dr, the small work done is dw. What will be the total work done? Integrate it between the limits r to p. So you are moving from r to p. So initial point is r, final point is phi. It is a finite integral. So r to p, F external force acting on a small element dr vector. When you add up all the work done, you will get the total work done. F external vector dot dr vector will give you dw. If all the dw are summed up between r to p, that will give you total work done. See how clearly an integration is involved in this particular case. W equals integral of r to p f external vector dot dr vector. This f external vector dot dr vector is the small, it will give you the small amount of work done. As you add up all the small work done between r and p, that will give you the total work done. This integration is nothing but summation. You are adding all the small amount of work done. So you are getting the total work done. W equals integral r to p f external dot dr vector. As we saw, the electrostatic potential energy or electrostatic force is a conservative force. Electrostatic force is a conservative force. It is independent of the path followed. Depends on initial and final positions. Depends upon initial and final positions. So what we can say is, at this particular point R, there will be a potential energy for this charge q prime. I can mark it as UR. At this point P, there will be a final potential energy. I can mark it as UP. So the potential energy at the point R possessed by q prime is UR, and the potential energy at the point P possessed by this q prime charge is UP. Then the potential energy difference UP minus of UR is delta U, which will be equal to work done. So change in potential energy is equal to work done. Work energy theorem once again. Change in potential energy is equal to work done. So this work done must be equivalent to potential energy alone, should not be equal to any change in kinetic energy. So UP minus of UR, U upsilon is the representation for potential energy. U stands for upsilon, a Greek alphabet. U upsilon. UP minus of UR equals delta U, which is equal to W. So I can write this expression as delta U equals UP minus of UR equals integral R to P F external dot dr vector. F external dot dr vector. What is the magnitude of external force here? F external is equal to F Coulomb, is equivalent to Coulomb force, which is equal to minus of q prime into E vector. In an electric field, you are moving the test charge q prime. So the force exerted over the test charge is given by minus of q prime into E. So F Coulomb is minus of q prime into E, F external is minus q prime into E vector. So this potential energy delta U is equal to integral R to P minus of q prime E into dr vector, E vector into dr vector. You just look at the case. Instead of external force, have substituted minus of q prime into E vector. So delta u equals r integral r to p minus of q prime E vector dot dr vector. Q prime is the test charge, which is a constant taken out of integration, minus of q prime or q prime integral r to p minus of E vector dot dr vector. Now, if you divide this potential energy difference, delta u is potential energy difference, up is potential energy at the point P, ur is the potential energy at the point R, delta u is potential energy difference. If potential energy difference is divided by the test charge, potential energy difference per unit charge, I can write this as a statement. Potential energy difference per unit charge is delta u divided by q prime. So delta u by q prime is equal to q prime integral r to p minus of E vector dot dr vector divided by q prime. This gets cancels out. So this will be simply equal to delta u divided by q prime is equal to integral r to p minus of E vector dot dr vector. And this delta u divided by q prime, potential energy per unit charge, is nothing but potential difference. This is equal to potential difference. This is equal to potential difference, delta u divided by q prime. Potential energy difference per unit charge is equal to potential difference. The potential energy difference per unit charge is nothing but potential difference, which is independent of q prime. This is equal to integral r to p minus of E vector dot dr vector. It is independent of q prime. So potential difference is independent of q prime, which is equivalent to the potential difference between the points P and the points R, which is equal to delta V. So I can write the same expression as Vp minus of Vr, which is equal to delta V. This is equal to integral R to P minus of E vector dot dr vector, minus of E vector dot dr vector. This expression is equivalent to potential difference between the 2 points P and R. And you can define potential difference here. Potential difference between the 2 points P and R or between any 2 points is defined as the amount of work done by an external force in moving a unit positive charge with a constant velocity from one point to another. So what is potential difference here? Actually, this Vp minus Vr equals delta V. This is equal to integral R to P minus of E vector dot dr vector. This is equal to delta u divided by q prime, which is work done per unit positive charge. Work done per unit positive charge. So we can define it. Potential difference between 2 points is equal to the amount of work done by an external force in moving a unit charge from one point to another point with a constant velocity. One point to another point with a constant velocity. So definition is very simple. Electric potential difference between 2 points is defined as the amount of work done by an external force in moving a unit positive charge from one point to another against the electric forces or against the repulsive forces. Now, we can write the expression delta V equals delta U divided by Q prime, or delta U equals delta V into Q prime. So potential energy and potential difference are compared. Potential energy is nothing but, or potential is difference is nothing but potential energy per unit charge. Potential energy per unit charge. Delta U equals delta V dot Q prime. So potential energy, potential difference has a physical meaning, whereas potential cannot, or potential has no physical meaning. Potential difference has a physical meaning. This one has a physical meaning. But potential at a point has no physical meaning. But potential at a point must be defined. potential at a point must be defined. How will you define it? It's very simple. Potential, in order to define potential at a point, we can say, we can take the point R at infinity, where the potential is 0. V at infinity is 0. V at infinity is 0. Potential at infinity is 0. So when you consider the distant point as infinity, then the potential at that point as 0. So from a reference point to 0, you are moving a unit positive charge. So I can draw the diagram here. A source charge is assumed. I am considering a point P. I want to define potential at this point P. So I have to move a unit positive charge from infinity to this point. From infinity to this point. So what is the value of potential at infinity? 0. So from 0 potential point, you are doing a work against the repulsive forces on the unit positive charge to move it to a point P. So the amount of work done will be stored as the electrostatic potential at this point. So the definition will be very clear. So potential difference has real physical meaning. Potential at any point has no meaning at all. In order to bring out or in order to define potential at any point, we need a reference here now, and that reference is made at infinity, and the potential at infinity is 0. So the definition will go like this. The potential at a point is defined as the amount of work done by the external force in moving a unit positive charge with the constant velocity against the repulsive force from infinity to that point. From infinity to that point. See the statement. The potential at a point is defined as the amount of work done by the external force. Amount of work done by the external force in moving a unit positive charge with the constant velocity against the electric force. Against the electric force from infinity to that point. From infinity to that point. So potential difference and potentials are posing a slight difference in their definitions. Electric potential difference is defined as the amount of work done by an external force in moving a unit positive charge from one point to another point against the repulsive force. Electric potential at any point is defined as the amount of work done in moving a unit positive charge from moving a unit positive charge by an external force from infinity to that point with a constant velocity. Infinity to that point with a constant velocity. So if Vr goes as 0, then we can simply get the expression, this one, as Vr is 0. So Vp alone will exist. Vp equals integral R or integral infinity to P minus of E vector dot dr vector. Because at R, the potential is, R is at infinity, where the potential is 0. So Vp equals integral infinity to P minus of E vector dot dr vector. This expression will give you the potential at a point due to a source charge. Potential at a point due to a source charge. Vp equals integral infinity to P minus of E vector dot dr vector. Based on this idea, we are going to calculate the potential at a point due to a point charge. Based on the results what we have obtained, we can speak about the important points here. 1. The potential at any point is dependent upon or depends upon the electric field due to the source charge plus Q and not on the test charge Q prime. So the potential at any point depends upon the electric field due to the source charge plus Q and not on the test charge Q prime. So while moving this test charge Q prime from one point to another point, it must be moved with a constant velocity, so that it should not impart any kinetic energy. The external force acting on this test charge Q prime should not be imparted with any kinetic energy. It must be moved with a constant velocity. So the external force acting on the test charge Q prime must be moved with, must make the charge to move with a constant velocity, which means it must it should not impart any kinetic energy to the test charge. Already I explained the reason why it should be moved with a constant velocity. If not, it will get accelerated. If it gets accelerated, it will produce an electric field. But the result shows the potential depends only upon the electric field due to the source charge. If it is accelerated, then another electric field will also come into play. Then the potential whose dependence will also brings a dependence with the field due to q prime. That should not happen. So the charge q prime must be moved with a constant velocity. Then that means that the test charge q prime should not be imparted with any kinetic energy, because the potential is wholly due to the potential energy possessed by the source charge, or potential energy possessed by the charge q prime. So kinetic energy should not be there. Kinetic energy must be 0. This is the first thing. And based on the result, what we have obtained, delta V equals delta U divided by q prime. Delta U is potential energy difference. Q prime is the test charge. Delta V is potential difference. This is potential difference. This is potential energy difference. This is test charge. So potential energy has got the unit joule. Charge has got the unit coulomb. So potential difference has got the unit joule per coulomb. But practical unit for potential difference is volt, named after the scientist Alessandro Volta. Now to honor him, this unit has been defined. Who invented battery or electric cells. So in order to honor him, the unit of potential difference is given volt. So the unit of potential as well as potential difference, both are volt. Whenever you express the unit of potential difference, it must be expressed in terms of volt. And for potential difference also, the unit is volt. Equivalent unit is joule per coulomb. And you can also derive so many number of equivalent units for volt. Fine. Next thing, apart from this potential energy, electrostatic potential energy and electrostatic potential difference, we have to find out the electric potential at any point due to a point charge based upon the distance. So the next heading is potential at a point due to point charge. Potential at a point due to point charge. Potential at a point due to point charge. Consider a source charge plus Q. It has an electric field around it. Actually, we have existence of electric field all around the source charge plus Q. But we are considering the field in only one direction. Now, we have to determine the electric potential at the point P. In order to determine the electric potential at point P, as we saw earlier, as per the definition, you must bring a unit positive charge from infinity. Actually, I haven't represented any point over here, which means it is infinity. I have to move a unit positive charge from infinity to this point by some external force against the electrostatic force of repulsion with the constant velocity. The amount of work done in moving that unit positive charge to this point P from infinity will give you the potential at the point P. Potential at the point P. So potential at the point P can be calculated with the expression minus of infinity to P, E vector dot dr vector. What is the value of electric field at any point due to a point charge? Already you might have seen in the derivations that the electric field due to a point charge at any particular point is given by the expression E vector equals q by 4 pi epsilon naught r square into r cap. If it is represented as a magnitude, then it is E equals q by 4 pi epsilon naught r square. If it is represented as a vector, E vector equals q by 4 pi epsilon naught r square into r cap. So the electric field vector at any point due to a point charge is E vector equals q by 4 pi epsilon naught r square into r cap. If you substitute this expression 2 in expression 1, we will have Vp equals minus of integral infinity to r. E vector is nothing but q divided by 4 pi epsilon naught r square into r cap into dr vector. Here we have to do some manipulations. What is this dr vector? It is the product of dr into r cap. As I mentioned earlier, a unit vector is vector divided by its own magnitude. A vector is magnitude of that vector multiplied by unit vector. Magnitude of the vector multiplied by unit vector. And the product, dot product of the unit vectors is equal to 1. R vector dot r vector is equal to 1. Dot product of unit vectors, two unit vectors is 1. So, instead of dr vector, I am going to write Vp equals minus of integral infinity to r q divided by 4 pi epsilon naught r square into r cap into r cap or r cap dot r cap into dr, because this is the dot product here, E vector dot dr vector. So r cap dot dr vector. Instead of dr vector, I have taken a dot product with r cap dr. What is r cap dot r cap? 1. So this expression will get transformed to minus of infinity to r q divided by 4 pi epsilon naught r square into dr. Now this integration must be simplified. So the potential at the point P is Vp equals minus of integral infinity to r q divided by 4 pi epsilon naught r square into dr. I can take q out, 4 pi epsilon naught out, integral infinity to r dr divided by r square. This can be taken as minus of q divided by 4 pi epsilon naught. Integral dr by r square is minus of 1 divided by r between the limits infinity to r. Since integral dr by r square is equal to minus of 1 divided by r. This is by expression r power minus 2 into dr. X power n into dx is x power n plus 1 divided by n plus 1. R power minus 2 plus 1 divided by r power minus 2 plus 1. So r power minus 1 divided by x power n plus 1 divided by n plus 1. Minus 2 plus 1, this is minus 1. So minus of 1 divided by r. By this integration or by this formula, I am rewriting dr by r square as minus of 1 divided by integral of infinity to r dr by r square as minus of 1 by r between the limits infinity to r. So minus of minus becomes plus, q divided by 4 pi epsilon naught between the limits 1 divided by r minus of 1 divided by infinity. Anything by infinity is 0. So potential at the point P is equal to q divided by 4 pi epsilon naught into r. Potential at any point P is given by the expression q by 4 pi epsilon naught r. When you compare electric field and electric potential, electric field at any point due to a point charge is q by 4 pi epsilon naught r square. Potential at any point is q by 4 pi epsilon naught r. As you know very well, E equals V divided by r. So if you write q by 4 pi epsilon naught r for V and r is there, so this becomes r square. You will get the value of electric field due to the point charge at the same point. So we can say here electric field varies inversely with r square at any point due to a point charge, whereas the potential varies inversely with r for a point charge at any point. So Vp equals q by 4 pi epsilon naught r. So this is the expression which gives you the potential at any point due to a point charge. What are the important inferences that we can make from this result? 1. Important points. 1. As we see here, the potential around a positive charge is positive. Potential around a positive charge is positive. So potential due to or V due to a positive charge is positive, so V is greater than 0. But V due to a negative charge is negative, so V is less than 0, which is given by the expression V is minus of q divided by 4 pi epsilon naught r. If it is for positive charge, V equals q by 4 pi epsilon naught r. If it is for negative charge, it is minus q by 4 pi epsilon naught r. Potential is greater than 0, which means potential is positive. For negative charges, potential is negative, V is less than 0. Second one, the description for the motion of objects is, or explaining the motion of objects is easy with potential and potential energies when compared to fields. This is applicable for all fields and all potentials. If you are moving an object of mass m from one place to another place, in order to explain the movement of the mass, we can use gravitational potential and gravitational potential energies instead of gravitational field. That is simpler. Gravitational potential and gravitational potential energies are simpler basis with which we can explain the motion of objects. In the same way, to speak about the motion of charges, we can use electrostatic potential and electrostatic potential energy, which is much simpler when compared to the same explanation which is done on the basis of electric fields. Then the third inference is that actually here the movement of or description of motion of objects is simpler with potential energies and potentials. Potential energies and potentials. And the third inference is that around a positive charge, if you speak about a positive charge, the potential near a positive charge is more. As you move away from the positive charge, the potential goes on decreasing. So simply to say, for a positive charge, potential is given by the expression V equals q by 4 pi epsilon naught r. V is inversely proportional to r. As r increases, V decreases. So as r increases, potential decreases. At infinity, anything by infinity is 0. So potential is 0 at infinity. For negative charges, V is minus of q by 4 pi epsilon naught r. So as r increases, potential also increases, and the maximum value of potential due to negative charge is 0, that too at infinity. So at infinity, potential is 0. Potential is 0 for both positive as well as for negative charge. But for positive charges, for positive source charges, potential near the source charge is more. As you move away from the source charges, potential decreases and finally becomes 0. As you move away from a negative charge, the potential keeps on increasing and will be maximum at infinity, which is equal to 0, because there is a negative sign. As we said earlier, potential around an isolated positive charge is positive and potential around an isolated negative charge is negative. Potential is positive near a positive charge, and it is more when it is close to, when the point is assumed close to the positive charge. Why? Reason is very simple. As we saw earlier, it is the amount of work done in moving a unit positive charge from infinity to that point. So you are moving a unit positive charge towards the positive source charge. From infinity towards this positive charge, if I say from infinity towards this positive charge, I am moving a unit positive charge, the amount of work done to move the unit positive charge to this point and to this point differs. The potential or the work done will be stored as potential energy or potential here, and the potential at this point is less. Potential at this point is more because the work done is more. As you move to some other point R, the work done is further more, so potential is more at this point R. So around the positive charge, the potential is more, very close to the point, or close to the positive charge or source charge. As you move away from the source charge, the potential keeps on decreasing. Whereas around the negative charge, there is no need of doing any work on this positive charge. The negative source charge itself will be pulling it. So the work done will be less when it is close to the negative source charge. As you are taking this positive charge away from this negative charge, you are doing the work against the force of repulsion. So at this point, the amount of work done is more. As you move away from this negative charge, the amount of work done will be keeps on increasing. So the potential will be more at infinity, and at close points the potential will be less. So this is how we have to explain. In a gravitational potential field, if you consider Earth, a mass always moves from high potential point to low potential point. This is a low potential point. A mass always moves from high potential point to low potential point in case of gravitational force fields. In the case of electrostatic field, the positive charges, test charges, I am speaking about test charges, positive charges in general always move from high potential region to low potential region. And negative charges always move from low potential region to high potential region. I can explain it with the diagram. You consider a positive source charge. This is a test charge. I am speaking about test charge. I can consider plus and minus, simple. Plus Q charge is a positive source charge. As I mentioned earlier, if I consider three different points, let us say P, Q, R, the potential at the point P is greater than potential at the point Q, greater than potential at the point R. So if I place a unit positive charge over here or simply a positive charge here, a plus Q charge will repel this positive charge so that it will move along this direction. So what happens here? A positive charge is moving from high potential region to low potential region in a given electric field due to a source charge. So in a source charge or around a source charge there will be an electric field. In such an electric field, if you place a unit positive charge or simply a positive charge, it will be always moving from high potential region to low potential region. Suppose if you place and I can consider a minus Q charge also, a source charge minus Q. Here also we are considering three different points P, Q, R. The potential at P is less than potential at Q, less than potential at R. If you place a positive charge, we can say it will be attracting, right? So if I consider the positive charge over here or a plus charge over here at the point R, it will be attracted by minus Q charge. So it will be moving along this direction. VR is high, VP is low. So the positive charge will tend to move from high potential region to low potential region. So whatever the field is, when you place a positive charge will always move from high potential region to low potential region. Consider a negative charge here. If it is a negative charge, what will happen? If it is a negative charge, I am placing a negative charge here. Negative charge will be attracted by the positive charge, positive source charge. So negative charge will tend to move towards the charge. If it is considered in this particular case, if I place a negative charge over here, negative charge will repel, the negative source charge will repel the negative charge, so it will be moving along this direction. So what I can say is a negative charge in both the cases always move from a low potential region to high potential region. See this one, for a positive source charge, VR is low potential, VP is high potential, and the negative charge moves from low potential region to high potential region. And in this particular case, for a negative source charge, VP is low potential, VR is high potential, so negative charges always moves from low potential region to high potential region. So these ideas are very important. We should know how a positive charge will move in an electric field, how a negative charge will move in an electric field. A positive charge always moves from high potential region to low potential region. A negative charge always moves from low potential region to high potential region. Now, if there are various charges given, for example, there are lot many number of charges, more than one charge is there. What will be the net potential at any particular point? Let us consider different charges. Let us say Q1, Q2, Q3, Q4 and Q5. At this particular point P, what will be the amount of potential? I can say point P is at a distance R1 from Q1, R2 from Q2, R3 from Q3, R4 from Q4 and R5 from Q5. As potential is a scalar quantity, we can sum up the total potential or sum of the potentials due to individual charges at that point P, then that will give you the total potential at that point. So I can write V total equals V1 plus V2 plus V3 plus V4 plus V5. So V1 is the potential due to the charge Q1, V2 is the potential due to the charge Q2, V3 is the potential due to the charge Q3. In the same way, V4, V5 due to the charges Q4 and Q5. And the point P is at distances R1, R2, R3, R4, R5 respectively. If you sum up all the potentials due to all the 5 charges, you will get the total potential. Not only for these 5 charges. If I am having an nth charge, let us say Q1, and the point P is at a distance Rn from Q1, then I can say plus Vn. So if I take an algebraic sum of all the potentials, I will get the total potential at the particular point due to the charge distribution. So the expression goes like this: V total equals K, which is the constant 1 by 4 pi epsilon naught. So K Q1 by R1 plus K Q2 by R2 plus K Q3 by R3 up to K Qn divided by Rn, and this is equal to, K is taken out, this is sum over I equals 1 to n Qi divided by Ri, Qi divided by Ri. I have taken a summation where I runs from 1 to n. I must be substituted as 1. So Q1 by R1 plus Q2 by R2 plus Q3 by R3 up to Qn by Rn. This is the meaning. Sum over I equals 1 to n, which means we have to substitute the suffixes as 1, then 2, then 3 up to n. This summation is expressed in this form. So the total potential at any point due to large number of charges at various distances R1, R2, R3 will be given by this expression: V total equals K into sum over I equals 1 to n Qi divided by Ri.